All right, so is everybody ready? And we're going to launch through activity series metals. Yes? Everybody happy with that? Okay. So, as our introduction to our electrochemical cell section, we have done what over the last 3 weeks or so? We did titrations, which is a focus on oxidation reduction. Thank you, Sam. All right. So we spent a whole lot of time doing a topic on redox, because redox, as we know, is to do with transfer of what? What are we transferring in a redox reaction? Electrons. Okay. So we are transferring. We're transferring electrons in a redox reaction. And hopefully you can make the connection between a redox reaction and if I had a battery on me, okay, what's happening inside of a battery, because that's where we're going with this topic on electrochemical cells. Okay, so if you can understand redox, you can understand electrochemistry. All right, the two go together. But there's always a but in chemistry. The first part of the section on electrochemical cells is what we're talking about today, which is the activity series of metals. And it stays permanently, look, can't even write that off, all right? Stays permanently on the whiteboard, okay? And you all get that if you've got a decent periodic table on the back of the periodic table as well, okay, as an extra. It's about the only thing you get for chemistry. This is the activity series of metals, all right? And as I've put on the little intro here, it goes from the most reactive metal down to what we would call the least reactive metal. Now, metals, as we know, can behave in two different ways from our redox knowledge. Metals can behave as reducing agents, or if they're gaining an electron, we know they're behaving as an oxidizing agent, okay? Because reduction is a gain, that means here it's behaving as an oxidizing agent if it's gaining electrons. But most metals behave as reducing agents because they want to what? They want to lose electrons to form an ion, because this is now a stable configuration. All right? So most metals will do this. So when we look at the activity series of metals, which is a little bit confusing, that one there, I'll just change that. This is just meant to that's just meant to be a continuation. I sort of ran out of room, and I wanted to continue that from there down. So the order of the metals then is from the strongest reducing agent to the weakest reducing agent at the bottom of our list. Okay? That's how we look at the activity series of metals. Everybody cool with that? Alright? So the most reactive, our activity is based on its ability to behave as a reducing agent or to undergo oxidation. All right, so the most reactive metals are at the top. Now, here is the most important part in relation to how we utilise it. We're going to do some reactions in a minute. I've got it set up, and we'll look at what actually works in terms of if I've got one metal reacting with another. Now, this won't make a lot of sense right now, because we've got the metal and we've got a metal ion, we've actually got a metal in this case, and a metallic salt mixed together in the same test tube. And I've got them ready to go. So we've got them together in the same test tube, okay? Well, at the moment I haven't, I've just got copper in here, all right? Physically, when we actually begin to do this from an electrochemical sense, we separate the two from one another. We have a metal electrode on one side of a battery, we have a metal electrode on the other, okay? We have solutions in these. This was a copper half cell. This would have copper sulfate in it, okay? If this is lead, it would have lead sulfate in it. And I have a salt bridge to separate the two. And then on the outside, I have something that's going to draw current, like a radio or a light or something. So this forms the basis of my battery. So when we talk about it in terms of an electrochemical sense, you'll see they're normally separated. We don't normally have our metals and our metallic salts, that is, in the same system, okay? We physically separate them. Now, what's the equation saying on the board? Because we have to understand the activity series of metals and how we use it to our advantage. What it says is this: if metal M is above metal N on the activity series, then they're going to react. Okay? And I'll say that again. This is a solid, by the way, all right? This is a solution, and solution I've just chosen a 1 positive charge here, but it could be a +2, it could be a +3, but any other metal, okay? So if M is above N on the activity series, then I'm going to get a reaction. What that means is that this metal, okay, will displace the other one. They'll swap places. So what was the solid initially will end up in the, okay, what was the solution initially will end up in the solid, and what was initially a metal, okay, will dissolve over time and it will end up in solution. Now it's probably easier to see than for me to actually explain it, okay? So we've got 4 scenarios here, and you're going to tell me whether we're going to get a reaction. So I've got copper set up in a test tube, and I'm going to add to copper silver nitrate. So the combination I'm looking at here are these. It's copper plus Ag plus. And the question is, will I get a reaction between copper metal and silver? How do I work it out? Oh, activity series, all right? Copper's here, silver's here. Copper is above silver in the activity series of metals. So based on what you just told me, okay, copper should displace silver. Let's have a look, okay? So here is my piece of copper, okay? I've got some silver nitrate thanks to our lab assistant. Yep, I've just got to grab it down the bottom there. Okay, and silver nitrate we have to be careful of because, anybody tell me why we have to be careful of silver nitrate? Oh, it's not an irritant, but it's not good, not really good. If we get it on our hands, they go nice and black in colour. I want to try and cover most. Actually, I guess I don't have to cover all the copper, because then it'd be interesting to see what's happening in that solution. All right, now, it's immediate change, I think there's going to be. It's already going quite dark in colour, all right? You probably won't be able to see that. If you can see, actually I've got some copper. This is the original copper, this one, and this is what's happening once I add the silver nitrate. See the difference? Can everyone out there see the difference? Okay, so here's the original copper, all right, and it's going dark, all right? It's not going dark. Can anyone tell me what it's actually doing? It's making, hands up again, what, who, what? It's making a, no, it was not precipitating anything. That was a year 10 reaction that I just did, year 10 practical. This is turning dark, it's displacing what? What am I making in here on the surface, and it's looking even prettier now? Silver. So I'm actually taking silver out of solution, okay, that was an aqueous solution, and it's actually forming crystals. I can get it on the camera there. It's actually forming crystals. There it is, okay? All right, now I'll get people to have a closer look at that in a minute, but that's actually what it's doing. So it's forming these little spiky crystals of silver straight away. So we know it works then. So, well, in one instance it does anyway. Let's have a look at another combination. Iron and copper sulfate, all right? I think I've got iron in one of these. Yep, here it is. So here is a piece of steel, all right? Or iron in this case, Fe. And I'm going to add to that copper sulfate. Copper sulfate is a blue solution. Iron and copper. Where is iron on the activity series relative to copper? Above? Okay. So iron is above copper? Yes. Are we going to get a reaction then? No. We should get a reaction, shouldn't we? All right. So we're going to cover the iron. Okay. We're going to let that sit for a little while. And what do you notice straight away? What's the colour of the iron? Can you guys see in the front row? the iron has, wherever the copper's come in contact with the iron, you can actually see, look, okay, it's gone brown on the surface. It's gone brown already. And what colour is the browny goldy colour? This is copper. This bit of iron now looks like copper. Okay? It's like it's magic almost. Alright? So I'm turning the iron into copper because the iron is displacing copper. They're swapping around. Okay? And if I left that, and I will leave it there, we're going to leave it there for a couple of days, what you'll find is that in time, the piece of iron will completely dissolve and I'll get this brown crystals in there, and the brown crystals correspond to copper. So here is my, so we've got, can you see the crystals from where you guys are sitting? Yeah. And I just touched it, so they're just falling to the bottom now. So that's silver. Maybe we could actually filter that and get some money from that. All right. So, and of course so these are two metal exchange reactions. That one's going gangbusters, that one's going gangbusters. That's good. Okay, next one. Lead, copper sulfate. We're going to get a reaction. We've got a piece of lead in here, okay? And I'm going to add to that one copper sulfate. Should I get a reaction? So lead is above copper sulfate on the activity series, not that one. But over here, lead, it's only just above it, just by one. But it doesn't matter how far above it is, okay? It's going to get a reaction, we hope. So we're going to add copper sulfate to our lead. And I think might take a little while, because what should I have done to the metals to make them react even better? I should have actually taken the oxide coating off the outside, and I've been handling them as well, so they're probably a little bit oily on the surface, and they're going to be a bit slow to react, but that will happen. All right, I'm confident that's going to happen. All right, next one. So far we've got a reaction here, we've got a reaction here, we've got a reaction here. All right, the last one. The last one, I've got a bit of copper. Okay, and I'm going to add to that lead nitrate. So am I going to get a reaction there? Okay, no, because the lead, okay, is not reactive enough to displace copper. Okay, if you look at it like that. So I've now got over here, all right, my lead solution, which apparently you aren't allowed to use anymore, because lead is a heavy metal. Apparently it's okay for me to use because I'm already damaged. Okay. So here we go, and we're going to just sit that for a little while. But I think you can see that the copper looks like. What does the copper look like? Copper. Okay. Nothing's happening in that reaction, which is what you predicted. So that really, all right, is what we were trying to show you. That this reaction will only work if this metal is above whatever that metal is, even though it's a metal ion. If that's above it on the activity series, we will get a reaction. So when we apply this to our electrochemical cells, okay, that helps us. Can anybody work out how come that helps us if we get a reaction? Can anybody see where it connects with electrochemical cells? Okay, of these two chemicals, which is undergoing oxidation and which one of these is undergoing reduction? I'll redraw the little picture. So what direction are electrons going to flow? Which one of these is behaving as an oxidizing, which one is undergoing oxidation, which one's undergoing reduction? M to M plus, is that reduction? Okay, it's losing electrons. So this is reduction here, okay, it's undergoing reduction, because up here, M to M plus, well, that's a reducing agent, isn't it oxidation? Okay, isn't that losing electrons? Yes? Alright, so that's undergoing oxidation, okay? The N plus, okay, is undergoing reduction. Reduction is gain of electrons. So here it is here. Okay, so which way are the electrons moving from the metals? What's our rules? Oxidation is loss. Reduction is gain. Okay, so where are the metals going from and to? Where are the metals? Where are the electrons, I should say? From M to N, yeah. Alright, so the electrons in the solution are actually moving in that direction. But the problem is they're in the solution. Okay, we don't want them to be in the solution when we take it to the next level when we look at our galvanic cells. Okay, we want the electrons to be actually moving not through the solution, but from one electrode to another. Okay, and so like I said before, we physically separate the two. Alright, going gangbusters just to show you. Alright, oh, fell off again. So here is the silver being produced. Okay, it's probably about $1 worth of silver there now that we've made. Okay. Here is what was originally a piece of iron, okay, and you can see the top of the iron up here. All right, that's it there. But we've got this brown copper being produced there. How much is copper a kilogram? This one's taken a while. This one should react, okay, with the lead, but it's taking a long time. I suspect because the lead's very oxidised. But we'll let it go for 24 hours and see if we get a result by tomorrow. It's got an oxide coating on the outside.
How would you get rid of it?
Scrub it off, or dip it in acid to delete the oxide. To remove the oxide, dissolve the oxide. Okay, that's how you would do it. All right. Any questions? That's it.